In this chapter, we will cover simple linear regression. In Chapter 2, we examine the relationship between interval variables via mathematical equation. We call this correlation. Now that was only the correlation between two variables, a y and an x. In this chapter, we will discuss how we can make that correlation more formal. That is, actually make a linear equation that describes the relationship for y and x. In the next chapter, we will discuss how we can extend this relationship to multiple x variables. So for example, when we think about the relationship with crime and police, what other factors may actually affect crime? For example, the unemployment rate, the socioeconomic situation in the city, whether or not there is sufficient jobs or education in the area. All these items can affect crime. How do we control for all of them at the same time? That's what Chapter 13 will be about, called multiple regression. But in this chapter, we will only look at the relationship between one dependent variable and one independent variable, which we will call x for now. This analyzes the specific relationship between the independent variables and the dependent variables. So let's consider a very simple relationship. We want to know how much a house costs given its size. Now most lots, that is an empty lot, sells for about $25,000. And building a house costs about $75 per square foot. So that gives us this linear relationship where house cost is the dependent variable, the slope is $75, and the x value is size per square foot. We also have a y-intercept, and this y-intercept is exactly at $25,000. You can assume that that is a house that has no size, or a size equal to 0. Therefore, it's an empty lot. An empty lot should have a value of $25,000, and for each square foot, we add an additional $75. So think about that for a second. If we had a home that had 1,000 square feet to it, and then we would actually add $75,000 to the $25,000, giving us a home of $100,000. However, house costs vary even among same-size houses. So we get this variation in the data. Each one of these points represents a home. For some homes, they could cost more even though they have the same size, or they could cost less. It's not a perfect relationship. What we're trying to do is find the line that best cuts through that data. Since costs behave unpredictably, we add a random component. The deviation between the line and the observation is called the error. These are some of the unobservable characteristics about a home that we can't explain using only two variables. For example, does the home have, say, a garage? Or does it have marble floors? Or is it in a more valued neighborhood than another one? So that's where this error term pops up. It captures all of the unobservables that also affect house costs but are independent of size. So our very simple linear regression is written as y is equal to beta naught, which is the constant, plus beta 1 times x. X is, in our case, our independent variable, plus an error term. Again, y is equal to the dependent variable, x is the independent variable, beta naught is the y-intercept, and beta 1 is the slope of the line. That Greek letter E at the end is the error term. Now, beta naught and beta 1 are unknown population parameters, and they have to be estimated. You can think of those as the mu's and the pi's of our previous chapters. The estimates are determined by drawing a sample from the population of interest, that is, going out to, say, Zillow.com and grabbing a bunch of homes, not all of them, but a bunch of them, and then calculating a sample statistic. We're trying to find a straight line that cuts in the data. The question is, what is a good line? Exactly, how do we find this line that cuts through the data? Any one of these are lines that cut through the data, but which one is the best line? The approach we take is we look at the line that minimizes the sum of squared differences between the point and the line. That is, we're trying to minimize the error term, minimize the variance of the error term. So think back to what our error term is. We have the actual observation, and then we have the amount that the line would predict. The deviation between those two is our error term. Now you can think of this as the stuff we don't know. And we want to minimize the stuff we don't know and maximize the stuff we do know. Now y hat here is actually constructed from our line. Okay, if we go back, here is our line. So we're going to go ahead and replace y hat with this part of the line. This is still our residual. Now the sum of squared residuals tells you the amount of variation in the data the estimated line cannot explain. Therefore, our objective is to pick beta naught and beta 1 such that we minimize that variance. So you want to choose the best constant slope that minimizes the amount of variation you cannot explain. So here are some observations. Let us compare two lines. So here we have the sum of squared deviations. You can see that this line basically cuts through the origin. Here's the second line. The second line is a horizontal line. And again, we calculate the sum of squared differences. In this particular case, the flat line, the second line that is, has a smaller sum of squared differences than the straight line, the one traveling almost through the origin here. Okay, so this is actually telling us that the diagonal line is worse off than the flat line, right? This 3.99 is less than 6.89. Therefore, the amount of stuff we don't know is less in the straight line than it is compared to the diagonal line. Now, this won't always be the case. Now, how do we choose the appropriate slope and constant? In order to do that, we have to do some calculus. What you can do is you can think of this relationship here as being a parabola that happens to open up like a U. And what we want to do is we want to find the coordinates of beta naught and beta 1 such as the U is being minimized. In other words, we want to find the very bottom of a cup and choose beta naught and beta 1 to make it as small as possible. So what we do is we take a derivative with respect to beta naught, treating beta 1 constant. When we do that, we get this relationship here. We do the same thing for beta 1, treating beta naught constant, and we get this relationship here. Now we have two equations and two unknowns, which we can solve. What we're going to do is first we're going to solve for the constant. So here we have that same relationship we had on the previous slide. What I'm going to do here is first, let's divide both sides by -2. If we do that, we still get 0 on the right-hand side, and we get a +1 on the left-hand side. Then I want to divide both sides by the sample size, n. So I'll get 1 over n, the sum of yi minus beta naught minus beta 1 xi. It's still going to be equal to 0 over here, which means that I can write it as the sum of yi divided by n, which is just the mean of y, minus beta naught summed up n times divided by n, which just gives us beta naught back again. And then beta 1 times xi divided by 1 over n, which gives us the mean of x. So now this is still all equal to 0, which means that we can bring beta naught over to the opposite side and find the relationship that beta naught is equal to y bar minus beta 1 x bar. Now using the previous relationship, we can now solve for the slope. So this was our equation for the slope, right? Here is our derivative of the variance with respect to beta 1. Again, we can multiply both sides by -2 and knock that out. But let's also plug in what we just found for beta naught. That is, we're going to say yi minus y bar minus beta 1 x bar, where this represents beta naught. And then we still bring down minus beta 1 xi and xi. If we rearrange some terms, meaning we group the y's together and the x's together, we get yi minus y bar minus beta 1 xi minus x bar, and all that's still being multiplied times xi. In this next step, we have to do a little math trick. And this math trick requires adding 0. You're going to notice that before we had just xi on its own. Now we're going to have xi minus x bar and plus x bar. When we do this, we're essentially just adding 0 to xi. But it's going to help us actually figure out the value of beta 1. And now what we're going to do is we're going to distribute just the first part out to each one of these parts. If we do that, we get our first term of yi minus y bar times xi minus x bar. And then we do it also for the back half. Xi minus x bar times xi minus x bar gives us xi minus x bar squared. Then, for the next component, we have to multiply this x bar times each one of those units, and that gives us this second equation. Now here's a couple of things I want you to notice. In the first part, we have this yi minus y bar times xi minus x bar divided by n. This should look a whole lot like a covariance to you, and it is. It's the covariance of y and x. Over here, if we were to bring this sum over and still have that division by n, this should look a whole lot like a variance to you, specifically the variance of x, and it is down here. The last thing we need to be able to show is that this last term here is equal to 0. Well, x bar is just a constant, meaning that if you sum up its values and divide by n, you get the same x bar over and over again. So we can actually pull this thing all the way out to the front. The next thing we have is we have to ask ourselves if the sum of yi minus y bar is equal to 0. Well, let's think about that for a second. The sum of yi is the same thing as saying n times y bar. Alright, go ahead and look at the formula for a mean. If you multiply both sides by n, you'll have n times y bar is equal to the sum of yi. Well, let's think about what the sum of y bar is. The sum of y bar is just n times y bar. So these two will actually cancel each other out. The same is true for this xi minus x bar. So this whole term will go to 0, leaving us with beta 1 is equal to the covariance of y and x divided by the variance of x. This allows us to write down our estimates now as little beta 1, which is our point estimate for beta 1, or b1, I should say, is our point estimate for beta 1, which we write down as the covariance of y and x divided by the variance of x, and beta naught, or I should say b naught, is equal to y bar minus b1 times x bar. And that gives us our regression equation. Now let's do this in an example. Here we have a car dealer who wants to find the relationship between the odometer reading and the selling price of used cars. He chooses a random sample of 100 cars and then he records their odometer readings and their prices, and he tries to find the regression line. So first, let's try solving this by hand. I'm going to give you some values. Here is x bar, here is y bar, here is the covariance of x and y, and here is the variance of x. Try to find for me beta naught and beta 1. Well, beta 1 should be pretty easy. We know it's going to be this value here divided by this value here, because it should be the covariance of x and y divided by the variance of x. We then use that information in our formula for beta naught. Recall, that's y bar minus your estimate for the slope times x bar. So when we do that, we find that beta 1 is equal to negative 0.06232, and beta naught is equal to $17,067. So how do we interpret these two values? Well, this would say that if the car had no miles, the value of a new car would be $17,067. And for each mile we drive, we lose about 6 cents. Now we could do the same thing in Excel. We could go use the same data and we can estimate it in Excel. And Excel will give us the following output. Notice it gives us our intercept. It gives us our slope, which is exactly what we've previously found. It also gives us standard errors. These standard errors are similar to the ones we've used in the past in order to find t-statistics. You'll notice that if you take this coefficient and divide it by this standard error, you should get this t-stat right here. Same thing is true with this coefficient, and you divide it by its standard error, you'll also get this t-stat here. Lastly, you'll get the p-value associated with these coefficients equal to 0. In our case, they're highly significant, where even at the 1% level, we can reject the null hypothesis that these values are different from 0. There is some additional information that is given to you in these tables, which we will discuss further in the next coming slides. Now, one thing we need to be careful about, that even though we can interpret this relationship of the line as a brand new car having a value of $17,067, the problem is we have no data that actually exists out there. In other words, we have no data for cars between 0 miles and our smallest mileage amount. These are all used cars. We have to be very careful to not want to apply these values out here because our data does not exist. It's outside of the bounds of our model. Doing so would be quite dangerous. In other words, you could be making very, very poor predictions when it comes to cars for which you have no data. Now, for cars for which lie inside of your data set, these are pretty good predictors. So this slope of the line for each additional mile on the odometer, the price decreases by an average of about 6 cents. We know it decreases because we have this negative sign here. If it was positive, it would be an increase of about 6 cents. Lastly, we have this error term. In order for these results to be unbiased and consistent, the error term must satisfy certain conditions. The 4 requirements involving the distribution of the error term must be: 1. That the probability distribution of the error term is normal. This allows us for us to use a t-statistic. The mean of the error term must be equal to 0. This typically holds whenever you include a constant within your regression. Number 3, the standard deviation of the error term must be the same for all values of x. This is called homoscedasticity. If you violate it, it would be called heteroscedasticity. An example where this is violated quite a lot is when we try to look at the relationship between the amount saved, and the income of an individual. For certain people who are, say, very thrifty, their savings could be quite high for the same amount of income that they have as someone else who spends a whole lot. Their savings may be very low. The problem is that this relationship gets exasperated as income gets higher and higher. When you're very poor, you're already spending quite a lot in order just to keep up with your necessities. But as you get more and more income, your amount of disposable income increases as well, which means that you have more room to maneuver in order to move things either into savings or to spend it for leisure. So as income rises, the variance associated with the error term also rises. In other words, if X is income, the variance associated with the error term and X is increasing. Here we would violate the homoscedasticity property. Lastly, the set of errors associated with different values of y are all independent. That means each error is independent of another error. One person's odometer reading, say on their car, cannot affect the odometer reading on a different person. So from the three assumptions, we have y is normally distributed with a mean equal to the regression line and a constant standard deviation throughout, which is the same thing as saying we have this normally distributed variance around our curve. So this gives us some bounds over how far can an observation deviate from the line. It also helps us give us expectations for y, given different values of x. Now, if we had heteroscedasticity, what would happen is that as x increases, these distributions would get flatter and flatter, meaning that the amount of noise is going to be increasing with x. However, when we have homoscedasticity, you can see the shape remains the same. Assessing the model. The least squares method will produce a regression line whether or not there are a linear relationship between x and y. Consequently, it's important to assess how well the linear model fits the data. Several methods are used to assess the model. All are based on the sum of squares of errors. The sum of squares of errors is essentially the variance of our error term. This is the sum of the difference between the points, the observed points that is, and the regression line. It can serve as a measure of how well the line fits the data. If the SSE is very large, that means that our data are not fitted well by the line. But if the SSE is very small, that means our line does a very good job of predicting the points in the data. The standard error of our estimate. The mean error is equal to 0. If sigma is small, the errors tend to be close to 0, meaning close to the mean error. Then the model fits the data well. Therefore, we can use sigma of the error term as a measure of suitability of using linear regression. An estimate for sigma is given by SE. Now, SE is equal to the sum of squared errors divided by the sample size minus 2. This gives us the variance, or the mean squared error. The mean squared error would be the variance of the error term. Therefore, the standard deviation of the error term is its square root. We can calculate the SSE from our example before. You can see that our sum of squared errors is going to equal 9,000. We divide that by 98 because we had a sample size of 100. And we get an SSE of 303. Let's go back to the actual Excel printout so you can see these values. In this Excel printout, here is our SSE, sum of squared residuals. Here are degrees of freedom. If you take this SSE and divide it by 98, you're going to get the mean squared error, which is given by this box here. Same thing is true in the regression case. This is the sum of squared regression. If you divide it by its degrees of freedom, you get the mean squared regression, which is given by the value here. Next, we want to take the square root of this value. When we take the square root of this value, we should get the standard error, which is the 303 we just previously found. Another good measure of how well the data fits is by taking the sum of squared errors and dividing it by the total sum of squares. This tells us how much we don't know, how much of the variation in the data we don't know. So 1 minus that will tell us how much we do know. In other words, the sum of square regression divided by the total sum of squares tells us how much we do know of the variation in the data. That's given by the value called r squared. In this case, r squared is equal to 65%. That is, 65% of the variation in the data can be explained by the line. You should go ahead and check for yourself that by dividing by the regression sum of squares and the total sum of squares, you get 65. Likewise, if you take the sum of squared residual and divide it by the total sum of squares and take 1 minus that, you're going to get 65. Another way to test whether or not there is a linear relationship is to actually test the slope. Since this is a simple linear regression, we have but one slope to test. When no linear relationship exists between two variables, the regression line should be horizontal. In this case, we have a linear regression. Different inputs, x, yield different outputs, y, and the slope is not equal to 0. On the other hand, we could have cases where there's no linear relationship, meaning that for different values of x and y, we actually get a flat line. So the slope is equal to 0, meaning that y bar is just as good as predictor as using a simple linear regression. We can draw inferences about beta 1 from b1 by testing the null hypothesis that beta 1 is equal to 0 versus the alternative hypothesis, that beta 1 is not equal to 0. We set up our t-statistic just like we do before. We take our actual sample statistic, we subtract it from the null, and divide through by the standard error. The standard error in this case is going to be the standard error of the regression divided by n minus 1 times the variance of x. Now this is important here. This actually tells us something about the variation in x and why the variation in x is important. If the variance of x is very small, think close to 0, then this whole value gets very, very large, meaning that this t-statistic gets very, very small. In other words, it's harder to find significant results if your x variables do not vary by quite a lot, meaning they don't bounce around a sufficient amount. If they all seem to be clumped together, you're going to get a very small variance. And if they are very clumped together, that means your standard error is going to get quite big. In other words, we prefer lots of noise in our x. So let's go back and test. Test to determine whether there is enough evidence to infer that there is a linear relationship between the car auction price and the odometer reading for all 3-year-old Tauruses. Alright, well, let's go ahead and do that. We know from our estimate that beta 1 is equal to 6 cents, right? We know, because we've already calculated, that the standard deviation of the error term is 303.1. N minus 1 in this case would be 99 because we had 100 observations. And the variance of x was given to you, which we have here. This produces the standard error for your beta 1 estimate, which is the same thing we saw in our printout, the 0.00462. So now we apply the t-statistic, which means we use our sample statistic for beta 1, the negative 0.0623, our null hypothesis for beta 1, which is that it's equal to 0, meaning there's no relationship, and then our standard error. When we do that, we get the observed t-statistic of negative 13.49. In this case, the rejection region for t is going to be whenever t is greater than t of 0.025 or when t is less than negative t of 0.025. Here, our degrees of freedom are going to be n minus 2 because we have a constant and a slope, so we lose two values, which would be 98. Therefore, if we went to the t-table, we would find that that t-value is equal to 1.984. Now, given the 1.984, are we in the rejection region? Yes, we are. We are far in the rejection region, in fact. So we can overwhelmingly say that there is evidence to reject the null hypothesis. Our alpha, even at a 0.1%, would still be rejected given how small our p-value is. Our next measure of strength of relationship is called the coefficient of determination, but typically people refer to it as R squared. R squared is really a correlation term that is squared. If you remember back to the formula for correlation, we would have the covariance of x and y divided by the square root of the variance of x times the variance of y. Well, here we're just squaring both of those terms to get R squared. This is only true in the simple linear regression case. However, we have an opposite measure that we can also use that I previously talked about a couple slides ago, which is we take the amount of variation in the data we don't know, or the sum of squared errors, sometimes called the sum of squared residuals, and divide it by the total sum of squares. This tells us the percentage of the data that we cannot explain, which implies that 1 minus that amount tells us the percentage of the data that we can explain. So R squared here gives us an idea of how much of the variation in the data the regression line explains. The closer to 0 it is, the weaker the relationship it is. The closer to 1 it is, the stronger the relationship is. However, we have to be careful with using the coefficient of determination as the end-all be-all of this relationship. The reason is that there are certain situations which will lend itself to very high R squares and very low R squares, independent of really the relationship between y and x. For example, if you're talking about countries and you want to find out how GDP changes over time, well, GDP really doesn't change that much. So you should have very, very high R squares in the upper 90%. If you don't, then you have a very poor relationship. When you think about states and you want to find out whether or not the unemployment rate is has a large effect on state's GDP, then there you expect the relationship to be strong, but not as strong as at the country level. Therefore, measures somewhere between 30 and 60% are actually very good measures. However, when we're talking about people are very random, very different, where even R squares of 10% would be amazing. You'd be doing a fantastic job if you could explain an individual's behavior 10% of the time. So another way to understand R squared is to consider how we break down the variance of y. This first part is just the total sum of squares. These are the observations, subtracting off their deviation from y and squaring them. We can break this relationship up into two parts. The first part says, how much of y's variation do we not know? Remember, that is the observed amount minus the predicted amount. Plus, how much of the variation we do know, which is going to be the predicted amount minus y bar. These two can collapse back down to give you the total sum of squares. In our next step, what we're going to do is divide both sides by the total sum of squares. That's going to give us 1 on the left-hand side. It's going to give us this first term here, and this next term here. If we bring the first term over to the left-hand side, this gives us a measure for r squared, where this second term is how much we don't know, and then 1 minus that term tells us how much we do know. This term here tells us the sum of squared regression divided by the total sum of squares, which also gives us a formula for r squared. To understand the significance of this coefficient, note that the overall variability in y can be separated into two parts: the part that is explained by the regression line and the part that remains still unexplained, which is left in the error term. Two data points x1 and y1 and x2 and y2 of a certain sample are shown. We can separate up their deviation in two ways. The red part represents the total variation in y. The black part represents the variation explained by the regression line. That is, the difference between y bar and the regression line. The remainder is the error term, the distance between the point and the regression line. R squared measures the proportion of the variation in y that is explained by the variation in x. We can calculate that by the two ways I've pointed out before. R squared takes on any value between 0 and 1. R squared equal to 1 describes a perfect relationship where there is a one-to-one mapping between x and y. R squared equals 0 says that there is absolutely no relationship between y and x, meaning that they have a correlation exactly equal to 0. Using our computer output, we can see that 65% of the variation in the auction selling price is explained by the variation in the odometer reading. The rest, the 35%, remains unexplained by this model. So here's another application. This one is used quite a lot. It's called the CAPM, or the capital asset pricing model. One of the most important applications of the linear regression is the market model. It assumes that the rate of return on a stock R is linearly related to the rate of return on the overall market. I have a worksheet inside of our folders that you can play around with to find this on your own. In other words, this can actually help you make investment choices in the future. But let me just use this example here. R here by itself represents the rate of return on a particular stock. That is, take a time period, say 1 year, and look at how much return you would have gotten from buying a stock a year ago today and selling that stock at the end of the year. The difference in the price is going to be your rate of return. Beta naught here is supposed to represent the risk-free rate, what you would have earned regardless of investing in the stock market. RM here gives you the rate of return for some major stock index. So think of the Dow Jones Industrial Average or the NASDAQ value. And again, you want to know what the rate of return is. By how much did the NASDAQ go up over a year? By how much did the Dow Jones Industrial Average increase over a year? That then gives us a slope measure that we're going to compare these two values to. This is the beta coefficient measure and tells us how sensitive the stock's rate of return is to changes in the level of the overall market. Alright. In this example, I'm doing it for the Toronto Stock Exchange. Here we're going to be using the monthly percent return for the Nortel stock and the monthly percent return for the Toronto Stock Exchange. You notice that our intercept has an average return of right around 1.2%, which is quite small. Our Toronto Stock Exchange actually has a fairly large beta associated with the Nortel stock, and it's highly significant, which means that this particular Nortel stock is positively correlated with the Toronto Stock Exchange. However, we can only really explain about 31% of the variation in the Nortel stock exchange prices, given that we're using the total stock exchange. So there's still roughly about 70% of variation in the Nortel price exchange that we can't explain. So this is a measure of the stock market's related risk. In this sample, for each 1% increase in the Toronto Stock Exchange return, the average increase in the Nortel's return is about 0.88%. This is a measure of the total market-related risk embedded in the Nortel stock. Specifically, 31.37% of the variation in Nortel's returns are explained by variation in the Toronto Stock Exchange. In other words, 31% of the risk associated with Nortel is actually market risk and not firm-specific risk. For using the regression model, we need to assess how well it fits the data. If we are satisfied with how well the model fits the data, we can use it to predict values of y. There are two types of predictions that we're going to try to make. A point prediction, which assumes we're only looking at one specific value, and an interval prediction, which is very similar to our confidence interval. Let's predict the selling price of a 3-year-old Taurus with 40,000 miles on the odometer. The point estimate can be found by sticking in 40,000 in for x and solving out for the model, which in this case gives us $14,575. So that's our point prediction. But we might want to put some bounds around this prediction. How should we go about doing that? There are two ways of doing that. We can use a prediction interval or a confidence interval. The prediction interval is always wider than the confidence interval, for the prediction interval assumes you're only doing this step one time, and the confidence interval, like it's been done before, assumes that you are doing this process many, many times over. So the prediction interval will look very similar to the confidence interval in the sense that we have our point estimate, which is the $14,500 and change we found on the previous slide, plus or minus our test statistic, so either t or z, in most cases we're going to be using t, times the standard error. Only the standard error in the prediction interval is given by this full equation here. Notice this 1 right here. This 1 is not present when we talk about a confidence interval. It actually disappears. And the other thing we notice is that the size of the standard error is dependent on how far we are from the mean of x. So if we try to make or take values of x that are very, very far from the center of its distribution, the standard error actually gets larger and larger. Think back to when I said that we wouldn't want to actually use this model to predict the price of brand new cars. We don't have any x's that are in that area, meaning that this deviation would be very, very large, and our standard errors would be very, very large, potentially even crossing 0. The same holds true for confidence intervals. The further we are from x bar, the larger the standard error becomes. However, the confidence interval will always give a smaller range than the prediction interval because it doesn't have that +1 sitting in the front. Provide an interval estimate for the bidding price on a Ford Taurus with 40,000 miles on it. And we're going to do the two different types. First, the prediction interval. We already know that our y is going to be equal to that 14,575. Next, we need to find a t associated with 0.025 and 98, which we previously found to be 1.984. The 98 again here is the degrees of freedom. Next, we need to calculate this next term. Well, the SE we already found to be 303.1. The 1 is just the one that's here. N is 100 because we have 100 cars in our sample, so 1 over 100. We have 40,000 minus x bar. Well, x bar we found to be 36,000 miles, 36,009 miles. We want to square that deviation, and then divide that by 99 times the variance of x. That's going to give us a prediction interval that is $605 above and below our point estimate. We can do the same thing for our confidence interval, which doesn't include the 1, but all the other values are the same. And here, our interval will only be $70 above and below. Again, notice that the confidence interval is much tighter than the prediction interval. Now, to illustrate why we get this increase in the confidence interval and the prediction interval as we deviate from x bar, let's look at our regression line. When we are exactly at x bar and we use x bar as our point estimate, our confidence interval will be represented by just that black line, that black lift. Right? We only really have this one part here in the standard arrow. This last part, the second term, gets canceled out since xg will be exactly equal to x bar. If we decide to go one up and one down from x bar, then our confidence interval increases, because now we need to include this additional term within our standard arrow. We can do this again for 2. And if we want to, we could do it for 3. You can see that our confidence bounds start stretching the further and further we get from y bar, and it does it in a nonlinear fashion. In other words, it starts showing much stronger growth the further and further away we get. So we only really want to use our regression model to make predictions for values that can be found within our data set. The coefficient of correlation is used to measure the strength of associations between two variables. The coefficient value ranges between -1 and 1. It is exactly that. It's a correlation. So if r is equal to -1, you have a perfect negative correlation. If r is equal to +1, you have a perfect positive correlation. And if r is equal to 0, there is no linear relationship between the two variables. We can test whether or not the coefficient of correlation is significant by using the following test statistic. Rho here would be our correlation parameter. Our null hypothesis is that there is no relationship, so rho is equal to 0. An alternative hypothesis that rho is different from 0. We can use the following test statistic, which is going to be t is equal to r times the square root of n minus 2 divided by 1 minus r squared, where r is the sample coefficient of correlation. In other words, the covariance of x and y over the variance of x and the variance of y. Sorry, the standard deviation of x and the standard deviation of y. You can find this value by taking the square root of the r squared. This statistic is a student t with degrees of freedom equal to n minus 2. So let's look at the foreign funds index funds. A certain investor prefers the investment in an index mutual fund and constructed by buying a wide assortment of stocks. The investor decides to avoid the investment in a Japanese index fund if it is strongly correlated with an American index fund that he already owns. From the data shown in the index XLS, should he avoid the investment? So here's our solution. The problem's objective is to analyze the relationship between two interval variables. The two variables are observational, which are their returns. We are interested on whether there is a linear relationship between the two variables. Thus, we need to test the coefficient of correlation. We set up our null hypothesis, and we're going to solve this by hand. Our rejection region in this case is going to be if t is about 2, so if t is greater than or less than 2 or negative 2, then we're going to say that we're going to reject the null hypothesis. Our sample coefficients are going to be the covariance of x and y, which is 0.012, our standard deviation of x, which is 0.05, and our standard deviation of y, which should be 0.0512. When we do that, we calculate r to equal 0.491. So there is some positive correlation between those two values. And then we stick that into our formula for our t statistic, which ends up being 4.26. Now 4.26 is greater than 2.0, so we would say that the rho here is different than 0. So there is sufficient evidence at the alpha equal to 5% to infer that there is a linear relationship between the two variables. Alright, one problem that we're going to have with simple linear regression is that we can have some unusual observations. Observations that are extreme values. In some cases, these observations could be just a simple clerical error. Someone added in an extra zero, making your income from 10,000 to 100,000. Or they could be very important observations that we're just missing. Outliers are defined as any observation that is 3 standard deviations away from the mean. Now the reason outliers can be a problem is that they can, by themselves, affect the slope of a line. Let's look at this relationship between GPA and time spent on the internet, time spent online. For the most part, our observations are clumped up down here. But there are these 3 observations that seem to be a bit far away from this larger group. When we look at those observations, those 3 or these 2 in particular, if we were to remove them, let's see what happens to the line. Now you notice that the slope becomes stronger, meaning that before we had an insignificant relationship or almost a flat line, we now have a significant relationship. So we'd want to look at those 2 observations and find out whether they are in there due to clerical error or if they really belong. Sometimes we have to be careful that there is a relationship between x and y. It just happens to be a nonlinear one. So for example, here we have very clearly a U-shaped result. But using a simple linear regression line would lead us to believe that there is no correlation between the 2 values. Here are 4 different data sets, and they all produce the same exact regression line. And yet you can tell pretty easily just by using this dot plot here that they may not all be from the same relationship. So for example, this one here looks more traditional. The values are all bouncing around at about an even rate around the regression line. But here, we see that we really have a nonlinear relationship and we could do better than this simple linear regression line. In the next 2 cases, we see that outliers could be potentially biasing our result. If we were to remove this line, this little outlier here, you can see that our regression line would become flatter and actually would go right through all those points. Same thing here. If we were to get rid of this outlier, which clearly is far away, we would see that there is almost no relationship between x and y. And this would be a vertical